Dear students, welcome to this lecture in Digital Logic and System Design. Today we are going to continue with the discussion on the Karnaugh maps or K maps. We've already seen 2 variable, 3 variable, 4 variable K maps. Today we will see 5 variable K maps. So just as we had seen the 4 variable K maps, the 5 variable K map will be extended to include 5 variables. The name of the variables could be anything. For example, we have taken A, B, C, D, E. So on this side, it is very similar 0, 0, 0, 1, 1, 1, 1, 0. Again, emphasizing that every successive row has to, its label has to vary in just a single bit. So it is more like the reflected code or the gray code that we've already seen. On this side, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0 0 0 1 1 1 1 0, and then the mirror image of it 1 0 1 1 0 1 0 0 with zeros on all these sides and ones on all these sides, so as to ensure that this is in gray code, which means every successive column is going to vary in a single bit only. So correspondingly, when we are going to populate a 5 variable K map, the min terms may be numbered like this: 0 1 2 3 4 5 6 7. You can see this is 0 0 1 1 1, so this is 7, 8 9 10 11 12 13 14 15, then 16 17 18 19 20 21 22 23, then 24 25 26 27 28 29 30 31. Now whenever we have to combine, not only we have to we will take an example later. Not only we will combine the adjacent ones horizontally or vertically, taking the largest possible number of min terms in powers of 2, but also we will take terms which are, reflective of this. For example, we can combine 11 27 15 31, like that, or we may even combine like 9 11 25 27 13 15 29 31. So we can combine terms like this also, in addition to what we had been doing previously. We will take an example in a later slide. A 6 variable K map will extend in both the directions, with the variables being A, B, C, D, E, F. So this is something that we've already seen in the 5 variable K map. The 6 variable K map will have these variations in much the same way as we have for the columns. We'll have a similar thing for the rows, right? Now in this case, it may be combined not like this but also like this. For example, we can combine 9 11 25 27 15 13 15 29 31, and also, you know 41 57 59 43 45 61 63 47 all together. So that'll be like 4 the 16 terms can be combined together, in addition to the cyclic combination, in addition to the corners being combined, in addition to the adjacent ones that we combined. We can also have this as a reflector, and the combination of the reflected min terms can also be taken up. Let me take an example for a 5 variable K map in order to make things more clear. Suppose a 5 variable function is given with the min terms being these. So first of all, we need to populate these min terms in the 5 variable K map. So 0 2, like 0 1 is not there, 2 is there, and 3 is not there. Then 4 is there. You see, 4 is there. And then 5 is not there, 6 is there. So the 6 comes here. Then 7 is not there. Then I come here, 8, 9. 9 is there, right? 10 is not there, 11 is there. So I put a 1 here. Then 12, 13 is there. 12 is not there, 13 is there. Then 14 is not there, 15 is there. So they are, populated over here. Then 7, see, 15 is here, then 16 is not there, 17 is there, so a 1 there. Then 18 19 are not there, 20 also is not there, but 21 is there, so a 1 here. then 22, 23 are not there, then 24, 25 is there, so I've placed a 25, then 26 is not there, 27 is there, so I've placed a 27 here, and then 29 is not there, yeah, 29 is not there, 30, yeah, so 25, 27 that I've taken. So if I go back, I'll see this one, yeah, sorry, this was 28, so 28 is not there, 27 we already done, 28 is not there, 29 is there, then 30 is not there, and 31 is there. So that is how we can populate these min terms in the 5 variable k map. Now how do I combine them? First of all, I must look for the largest possible combination. So I told you that we can look at the combination which is a reflective image across this axis. So I can see that I can combine these four ones along with these four ones, so that will be the largest possible. So largest possible in powers of 2, this is in powers of 2 because 8 can be combined. Now what do I get when I combine these 8? So A gets eliminated, I get a B. So see, I've got a B here, and again over here you see that what all are varying, you see what all are varying. C and D are varying, 0 0 0 1 1 1 1 0. So C D both get eliminated. It is only E which remains constant. It is only E which remains constant, and that remains constant as 1. So I'll get BE. So that will be the first term coming out of these combinations of 8 ones. Now let me look for the second largest possible combination. So I can see that second largest possible combination is these two ones and these two ones put together. So four ones put together. Again, over here I get an A, B gets eliminated, so I get A here. And in these two, I see that what is constant is D and E, but D is 0 and E is 1. So this will be D dash E, right? So A D dash E is the product term, minimized product term that I'll get out of these four combinations, a combination of four ones. Now, is there any other place that I can combine 4 or 8 or beyond? No, right? So I must look for combinations. What all ones are remaining? You see, these ones have been covered, these ones have been covered, they are remaining, right? So I can combine them all four together. Why all four together? Because they are combining because of the reflective thing, and these two are combining because of the cyclic nature. So when these two are combining and these two are combining, so all four can be combined together. Okay. So when I do that, you see this is constant. So A bar, A dash, B dash, A dash, B dash is here. And then I see that only E is constant as 0. So E dash. So that is how I need to combine in 5 variable K-map. You must have started sensing that beyond 4 variable K-map, visualization of the combination of ones which can be combined together becomes a little difficult. And it is even more difficult when we reach 6 variable K-map, as we had seen in the previous slide, 6 variable K-map, because now you have to see not just like this combination but in all 4 quadrants, and that becomes really complicated. Beyond 6 variable, it becomes impossible to do using K-map. So we will have to look for some alternative ways to minimize functions which are having more than 6 variables. Even 6 variables or 5 variables becomes very difficult when we are doing using K-map. So we will look for some alternate way for minimization a little later. What I propose to do now is, so far we have seen using K-map only the sum of product simplification. Can we do product of some simplification also? Yes, we can. Because in product of some simplification, we have seen in the previous one of the previous lectures that zeros have to be combined rather than ones. So if I'm given a function in sum of product form like this, then what I can do is I can populate it using ones. So you see 0, 1, 2, 5. So 0, 1, 2, 3 is not there, 4 is not there, 5 is there. So a 1 here, right? So this has to be a 4 variable K map because just 4 variables, right? So 5, 6, 7 is not there, 8, 9 are there. So they are placed as 1, 1, right? 8, 9, 10 is there. So a 1 here, and 11 and beyond, they're all zeros, right? So they will not be placed. So what I can do is that I have populated ones. Had I been doing sum of product simplification, I would have combined these ones together. But now my problem is such that I have to do the product of sum simplification. So what all are not populated by ones, they will get populated by zeros. You see, this possibility is either 1 or 0. So the remaining ones will be populated by zeros, and then I can combine the zeros together. So that is how I can do combining zeros together. So first, let us see for the largest possible combinations of zeros. Zeros because I'm talking about product of sum simplification, right? So you see this is 1, 1, and I can combine these 4 zeros together. There's nothing bigger than 4 zeros that I could combine here. So 4 zeros together. And this is 1, 1. Remember, in product of sum simplification, it will be a bar or a dash, whatever, a dash plus b dash. So you see, a dash plus b dash comes from this. So in case of product of sum simplification, 1 corresponding to 1, I get a dash, right? Corresponding to 0, I get the true value. So a dash plus b dash will come, dot, that is ANDed. Another combination is this one, and this is c dash plus d dash, right? Then I can combine these these two zeros and these two zeros so as to get 4 zeros together. When I combine 4 zeros, you see a gets eliminated, it is b dash, so I get a b dash plus. Over here c gets eliminated because that is varying, and this is d dash, so b dash plus d dash. So that is how I can do a product of sums simplification, right? This, if I am combining zeros, I'll get a sum of product simplification. If I'm combining ones, I'll get a sum of product simplification, SOP simplification, that you can see for yourself. In fact, we have taken it as one of the examples earlier, but still you may want to combine ones and see whether I'm getting this. Next, I want to show how to realize these minimized Boolean functions using the logic gates that we've already studied. So first of all, let us do the sum of product realization. B dash and D dash. So B dash and D dash and it together. I get B dash D dash here. Then B dash C dash. Right. So I took this B dash and combined it with C dash using the AND gate. So I get B dash C dash over here. And then A dash C dash D dash. So A dash, I get C dash from here, and D, this is D. So I get A dash C dash D over here. I OR all three of them. So I get my F in sum of product form. If I want to do the same thing in product of sums form, and I've got the product of sums expression, so A dash plus B dash. So I get A dash plus B dash over here. C dash plus D dash. So I get C dash plus D dash over here. And then B dash plus D. So B dash plus D I get over here. I AND all of them, so I get F. So these are the two alternate ways of representing the same function in canonical, which was given to me in canonical sum of product form. Alternately, I can say that FABCD is equal to pi, that is product of what all min terms which are not there in SOP. So that will be pi 3, 4, 6, 7, then 11, 12, 13, 14, 15. So the same function can be written in the product of sums form, and I can correspondingly do its simplification. So using K-map, we just do not do sum of product simplification, we can do product of some simplification as well. And also one thing we note from here, that when we do the sum of product form, its implementation is and or implementation. In the first level we'll have all and gates, in the second level we will have or all or gates. In fact, we'll have a single or gate. So this is called and or implementation of the given boolean expression in sum of product form. This is or and form. Or and form is used for product of sums form of a given function. So I'll have all terms and the and term in the second. So SOP and or form, POS or and form may be realized using the. Now another conceptual thing, let us see. See, this is and invert, which is the NAND function, right? We have seen earlier, NAND is nothing but and followed by an inverter. So if I have got XYZ, so F will be XYZ whole dash, right? Now suppose I invert, right? I give the inverted inputs here, right? So this will be, and I convert it to a NOR, to an invert OR, right? So this is and invert, this is invert OR, right? So when I do invert OR, I'll get X dash plus Y dash plus Z dash. I'm feeding X here, so X dash is going in, Y dash is going in, Z dash is going in. So what I'll get out of here will be X dash plus Y dash plus Z dash, which using De Morgan's theorem I can write X Y Z whole dash, which is the same as the output of the NAND gate. So this may be an alternate representation of a NAND gate, right? Which will be rare, but then this is possible. Just as this is the symbol of NAND gate, this could be a symbol of NAND gate as well. This is an invert NAND gate and this is invert or NAND gate. Again, taking the same thing using two graphic symbols for NOR gate, right? Two graphic symbols for NOR gate. This is or invert NOR gate or followed by an invert. So XYZ, if I feed here, then I get X plus Y plus Z whole dash, right? Had this inverter not been there, I would have simply got X plus Y plus Z. Because of this inverter, it will be X plus Y plus Z whole dash. Now suppose I have an AND gate and I give the inverted inputs to it, invert AND. So it will be X dash Y dash Z dash, because feeding X here, X dash is going in because of this inverter. Feeding Y here, Y dash is going in. Feeding Z, Z dash is going in. So I'll get X dash, Y dash, Z dash. If I use again the De Morgan's theorem, this is nothing but X plus Y plus Z whole dash, which is the same as this one. So I can say that these are the two alternate ways of representing a NOR gate. This is OR invert representation of the NOR gate, which is very common. This is the invert AND representation of a NOR gate, which may be rare, but still that is a possibility, a theoretical possibility. Now, two graphic symbols for NOR gate, buffer, that is inverter. So I can simply take the AND gate, short both its inputs, and the output will be X dash, because what I'll get is X plus X whole dash, sorry, X dot X whole dash. So X dot X is X only, so it will be X dash. Similarly, or invert, suppose I have 2 3 whatever number of inputs here. If I short all of them and feed X there, so I'll get X plus X plus X plus X as many times as the number of inputs whole dash. Now X plus X plus X as many times as you want to do, that will remain X. So finally I'll get X dash. So this also gives me an idea or a concept which is said to be a functionally complete gate. A functionally complete gate is the one by using which you can realize all the basic Boolean operations. There are three basic Boolean operations: AND, OR, and NOT. Now, AND alone cannot give you OR. or alone cannot give you AND. But NAND and NOR are such gates which can give you all three basic Boolean operations. Using NAND, a few NAND gates, you can get AND operation as well as OR operation as well as NOT operation. Similarly, using NOR, you can get both all three basic Boolean operations, OR, and NOT. So that is why NAND gates and NOR gates are said to be functionally complete gates. They're also called universal gates because using them you can realize all the basic Boolean operations, namely AND, OR, and NOT. Right. So moving on, we have seen the OR and OR implementation. Now let us see NAND NAND or NOR NOR implementation. Suppose this is the AND OR implementation, right? AND OR implementation. So what do I get? F here. F will be AB plus CD plus E, right? This will be AB, this will be CD, and this will be E. So F will be AB plus CD plus E. Now let us do a subtle thing in which let us place a bubble here and a bubble here, which means double inversion. And we know from one of the theorems that x dash dash is x. So putting a bubble here and a bubble here is not going to make any difference. It will be the same. No change in the function. Similarly, a bubble here and a bubble here will cancel out. So I'll still keep getting the same thing. So I'm just putting a bubble here and a bubble here, a bubble here and a bubble. Now over here, since this is a single input, so when I'm placing a bubble, this bubble I should give an inverted input here, E dash, right? So that after inversion I receive E only here, just as I was receiving E only here. Now this is nothing but the NAND gate, which we have seen in the previous slide. This is nothing but the NAND gate, right? Whenever you are giving the inverted inputs, this bubble comes out and the nature of the gate changes because of the De Morgan's theorem. So I can replace this by the NAND gate. So the same AND OR function can be realized using NAND NAND implementation, right? Where every gate is a NAND gate. So you see, this also helps. I don't have to worry about realizing different gates on a VLSI chip. I can realize the entire VLSI chip using the same type of gates, which is a NAND gate in this case. Similarly, can we do NOR implementation? Yes, provided that I've got the function in POS form and its implementation in OR AND form. This level is OR and this level is AND. So what do I get here? I get A plus B and C plus D and E. Now I am placing a bubble at both these places. That should not make a difference because that will cancel out. So placing a bubble here and a bubble here. Similarly, placing a bubble here and a bubble here. And finally, since I have to place a bubble here, so I must invert this also. Okay, right. So now this we have seen in the previous slide, but that this is nothing but the NOR gate. See, this is nothing but the NOR gate, right? So I can replace this by the NOR gate. So what do I get? I get NOR implementation. So the sum of product which is realized in AND OR can also be the NAND NAND, where every AND and OR gate is replaced by a NAND gate. If there is a single input, make sure that you have got NAND based inverter in place. Again, if we have product of sum simplification and product of sums expression and I have got its realization in OR AND, then in that case, if I replace every OR gate with and every AND gate with the NOR gate, my function will remain the same. So these are the alternate ways of realizing using logical gates the the NAND NAND implementation and the NOR NOR implementation. Okay. So now let us look at the rules for NAND NAND or NOR NOR implementation. Case A, function to simplify is f, and sum of products forms of what I have to get. So combine ones in the map. Sum of product, combine ones in the map. Implement with NAND, all NAND gates together. So I'll get number of levels, two levels will be there. Suppose I have to realize f dash and sum of products is given, then I must combine zeros in the map, because if f is given in sum of product form and I want to get the f dash, so I must combine zeros in the maps but in sum of products form. So I'll get NAND NAND implementation, and this will be a three level thing, just as I've shown here. Just as I've shown here, right? I'll come to it. Let me complete this table first. So again, realizing f in product of sums form, so either complement f dash in B, right? Or combine zeros in the map, just as we have done the product of sum simplification, and then realize the entire thing using NOR gates alone. That will be a two level thing. If you want to have f dash in product of sums, you know so complement f in a, this one complement f in a. So using De Morgan's theorem, you will get the complement of f in a. So the entire thing will be realized using NOR gates alone. This will again be a three level thing. Let us see how. Suppose I am given a function like this. Suppose this is a function where there are just two ones here, right? If I had to realize in sum of product form, then there is no way that these ones can be combined. They are diagonal, and diagonal elements are not combined, so they will be written as such: x dash y dash z dash. You can see here x dash y dash z dash, and this will be this should be a 1 here, in fact, that is missed. So 1 means 110, so that will be x y z dash, x y z dash. So this will be the sum of product forms. Now in order to, and what is f dash? F dash will be combining zeros in sum of product form, right? Because if f contains these two terms, which is m0 and m6, then f dash will have summation of m2, m1, m2, m3, m4, m5, and m7, right? So let us combine them. I'm note that I'm trying to get f dash in sum of product form. So even though I'll be taking zeros, but I'll be putting it in the sum of product form. So what is the largest possible combination? These fours. So 0 gets eliminated, and so does y. Only z remains. So I've written z here. So these four zeros are taken care of. Now in order to get this 0, I must combine it with this 0 in order to get better simplification. So it will be x, right? The one x and y dash. So x y dash, x y dash. I get out of this. Now combining these two, it should be x dash y. X dash and y. Z will get eliminated. So x dash y. So I've got both f and f dash. So in order to get the NAND NAND implementation, I see f in sum of product form, combine ones in the map and use NAND. So x dash y dash z dash plus x y z dash, and this is also the NAND gate, so I get f. In order to get f dash, this should be f dash. In order to get f dash, I should have x dash y plus x y dash plus z, and over here I'll get f dash. So this is f dash. In order to get f, I must have a third level, here. See, this is what I meant when I say number of levels to f is 3, because I'm starting with f dash. So with two levels I'm just getting f. If I want to, I'm getting f dash. If I want to get f, so I'll have the third level of just the inversion, right? So this was the rule for NAND NAND implementation. Okay. So probably I'll stop here. We've taken quite a few concepts, and try to go through it. If there are any problems, just email me to see to seek my clarification. So I'll be very happy to clarify. So please go through this lecture, and from this on we will cover in the next lecture. Right? Thank you very much.